morning session with Brian Page, giving us an overview of jets at EIC. Please, Brian.
Thank you. And thanks to the organizers for inviting me here to come give an overview of jets at the EIC. So I'll give a brief outline. I'll start with a quick introduction to the science we want to do at the EIC, as well as a little bit of history of jet measurements at the EIC, and then going through some high-level advantages of those observables. Then I'll talk about a few select measurements, which I think highlight some of the attractive features of jets. And then I'm going to detour a bit into what I call some practical aspects of jet measurements at the EIC. So going through the kinematics that we can expect, looking at the detector considerations that come from doing these measurements, and then finally something that is rather unique to our machine, looking at the crossing angle and what that implies for these measurements before I come to my conclusions. So I believe Alka showed this slide at our in the first talk of this meeting. These are kind of the high level pillars of EIC physics. So very broadly, what we want to do with this machine is study how, for example, the C quarks and the gluons and their spins are distributed within the proton and the nuclei, and then how the nuclear properties emerge from their interactions. So of course, things like spin and mass are dynamical properties of the proton, and we want to understand how those dynamics lead to the properties that we see. And then how do colored charged quarks and gluons and jets interact with the nuclear medium? So how do confined hadronic states emerge from the quarks and gluons? And then how the quark-gluon interactions help create the nuclear binding. And finally, a very exciting aspect is looking at the dense nuclear environment and whether or not we can see a new state of matter, which is the gluon saturation. So to do all this, we need what I like to call the ultimate or an ultimate QCD microscope. So we need precision measurements that come from the fact that we're using a leptonic probe. We need kinematic reach in order to fully explore the phase diagram, and we need high luminosity in order to properly look at various rare probes and get the statistics we need. And finally, we need polarization, because I think has been said by many people, if you don't understand spin, you don't understand QCD. So we also need a state-of-the-art detector in order to take advantage of the collisions that the machine is going to provide us. So we need wide coverage, not only in the central region, but far forward and far backward, with precision tracking, good PID, calorimetry over the full range of the central detector. And then finally, we need actual observables to connect the events that we measure in the detector with the physics that we want to do. And so hopefully today I can convince you that jets will be one of these observables that help us get to the physics that we want to do at the EIC. So just a real brief history. So of course, jets were kind of an afterthought originally when the EIC when the science case for the EIC was being developed. Initially, there wasn't much work on it. They were mentioned in passing in the white paper. And there was kind of an attitude of, well, you know, the EIC is going to be a relatively low energy machine. Will jets, you know, even make sense to measure? And then we have, you know, of course, CITES, and will, you know, jets are, for a large part, basically just, you know, clustering the particles you'd see in a standard CITES event in a new way. So would they be redundant? And I'd say in the last, you know, 10 or so years, we've seen a significant uptick in interest in jet physics at the EIC. You know, you see this from an increasing number of papers, and this is actually somewhat of an old plot of just the number of papers that mention or deal with jets at the EIC. There was a dedicated treatment of jets in the users group yellow report that went through the physics and detector needs for the EIC. A number of workshops, you know, the fact that we have jet groups in all of the proto collaborations and now the EPIC collaboration. And all of this activity is driven, I think, by the realization that jets will have a robust and unique role to play in the EIC science program. So what makes jets a useful probe? Well, they have several properties which really, I think, will be an advantage at the EIC. For one, of course, kind of the zeroth order is that they're well understood, both theoretically and experimentally. They're excellent proxies for the underlying parton kinematics. So of course, you know, in DIS, you can measure the event kinematics from the scattered lepton, but there are cases where you really want to see, you know, kind of see the result of the parton in the final state. And jets are kind of the best way we know how to do that. And of course, jets have substructure. They shower, and the shower probes QCD from the earliest times to the latest times. So you can explore the dynamics of QCD at different time or angular scales, all within the jet. And we have tools that we understand, precision tools that allow us to do this. And this is of course substructure. And so I mentioned the yellow report before, and if you go in and look at the document, there's a section that goes through the science case, and it's divided into a number of subsections looking at various aspects of the physics that we want to do. Things like global properties of the parton structure and hadrons, multidimensional imaging of the nucleons and nuclei. So this is TMDs, GPDs. Using the nucleus actually as a laboratory for exploring QCD and understanding hadronization. And so, of course, the fact that they're well understood impacts all of these measurements. Of course, this is kind of the zeroth order thing that you need for a successful observable. Being an excellent proxy for the underlying partons, this is very useful for global properties and multidimensional imaging. Moving on to the fact that we have these showers, you can look at the modification of these showers to learn about the properties of the nucleus, as well as understanding hadronization. And of course, the substructure plays into that as well. And actually, if you talk about things like particles within a jet, you can actually extract some TMDs from that as well. So before I go into the physics measurements themselves, I just want to briefly review some of the relevant sub-processes that form jets. So we have, of course, the leading order Born process here of deep and elastic scattering, where you have your virtual photon interact with your quark, and this gives rise to one jet that we detect, and then of course there's a beam remnant that goes down. But so this is kind of the dominant process. This is, far and away the largest cross section. And so a lot of the measurements that we'll look at, jets arise from this process. Of course, you can also have the higher order corrections, QCD Compton, and especially photon gluon fusion. So these kind of events actually give rise to two jet events, where these jets are largely back-to-back in azimuth with respect to now the virtual photon direction. So for example, if you go into, say, the bright frame, where you define your z-axis as sitting along the photon quark interaction line, and then try to cluster jets, these events will give you two back-to-back high PT jets in your event, and that's a pretty sure signature that you're looking at something like this or like this, depending on where in Q squared you are. And then as we go down in Q squared, towards Q squared equals 0, the hadronic component of the photon, the virtual photon itself, actually becomes important, and you get fluctuations into hadronic states, and you can actually get something kind of akin to proton-proton, or partonic 2-to-2 scattering, where you have a parton from the photon and a parton from your proton coming in, and again giving you this kind of dijet configuration. You also have, jets can also arise from things like diffraction, which I will not talk about here today. So before I mention the yellow report and how kind of it was broken down into a number of different science areas, and so just to orient us, I'll try to go through in some kind of order some of the measurements that are associated with each of these. So maybe not every bullet is represented in this talk, but if you go through and look at the yellow report, you'll see that these topics were all touched on, or jets touched upon all of these topics here. So things like the unpolarized parton structure, the proton and neutron, and then analogously the spin structure. And I would add here as well, not only the proton and neutron, but the photon itself, which I'll talk a little bit about, diffraction, global event shapes, which is, I would say, not exactly a traditional jet, but maybe jet adjacent. So of course, one of the great questions that we want to answer with the EIC is how the spin of the proton emerges. And so this has been a question for quite some time, from the spin crisis in the 80s through the work at RIC, and now we hope to really nail this down with the EIC. Of course, the golden measurement here is going to be the measurement of the G1 spin structure, or the G1 structure function, and then the scaling of that to get to the gluons. But it's also important to look at different probes of this for systematic reasons, for just consistency checks, etc. And one of the things we can actually access this as well in both inclusive and dijet asymmetry measurements. So we see here a couple recent calculations of what the double spin asymmetry for inclusive jets should look like up to next to leading order. And here we see a projection that we did a number of years ago on the sensitivity for dijets to look at ALL. So again, this is here where you select this photon gluon fusion process. So you're looking at your gluon from your initial state, and then you look at the ALL for your dijet system, and you can look at ALL as a function of dijet mass and actually access the gluon spin. So again, this is a good complementary several complementary measurements that'll help us determine the spin of the proton. Kind of an interesting, I think it's a pretty cool measurement here, is access to the strange PDF by looking at charm jets in actually charge current DIS. So again, just because of the nature of the charge current interaction, you exchange a W minus here, and then if you measure your outgoing jet, and you actually tag a charm meson in there, you are relatively certain that you're looking at a strange quark from your proton. And so this was some work that was done for the yellow report, trying to resolve some discrepancies between what we think the strange content of the proton is. And of course, although it wasn't pursued, I think you could obviously do this for polarized to get at delta S and delta S bar as well. So that's kind of a nifty technique to get at the strangeness, I think. Another really cool measurement that was, when I came in, was kind of a revelation to me, that the photon actually has some structure and you can study it. So this is again looking at, now we're going to be in the trying to go to low Q squared to get into this photo production regime, where we're actually looking at the hadronic structure of the virtual photon. And so what we really want to isolate this process here, where we kind of have partonic 2-to-2 scattering. And of course you do this by going to low Q squared, but we still have background from these so-called direct events like photon gluon fusion, where the photon interacts in a point-like manner. And the power of using jets for this measurement comes in when you can reconstruct this this quantity x gamma, which tells you how much of the photon's momentum is being transferred to this interaction. And so, of course, for a direct process, this is going to be one. The photon is just a point-like particle, and it gives all of its energy. But in a resolved process, you again have some the hadron itself that comes out has some momentum fraction. And so if you reconstruct this quantity, you can actually make an experimental cut here and really enhance your resolved component. And the fact that the jets are a very good proxy for the outgoing partons allows you to get this nice correlation between the X gamma you measure and what it actually is, which allows you to do this separation. And so I mentioned these global event shapes, which again are maybe a bit expanded from what people usually consider a jet. But again, you can use your jet to define some of these axes in the event by which you measure all the particles of the event against. And I think this is just a natural evolution of jet observables into, instead of looking at a single area of the detector, looking over the full range. And so these kind of observables actually offer very high precision measurements that allow you to look at various non-perturbative of aspects, such as the strong coupling constant. So in the yellow report, we actually did a pretty thorough breakdown of how well we can actually measure these things given various experimental uncertainties. And from the theory point of view, you can constrain these things down to the roughly 1% level, and we should with some work, be able to get to that level experimentally as well, to access these things again, like the strong coupling constant. So moving on from global properties into multidimensional imaging, things like TMDs and the Wigner function. So a lot of the recent work in JETs have come about with the realization that you can access the TMDs by looking at these jet lepton correlations. So basically, here you're looking at the modulation of the jet direction versus your scattered lepton direction. And this allows you, for example, looking at an asymmetry like this, allows you to access something like the Sivers function. And you can actually do this. One of the advantages of this kind of measurement versus, say, like CITES, is you can actually just isolate the transverse PDF versus the transverse the TMD fragmentation functions. So you're looking at just the TMD PDF here without having to convolute it with the appropriate fragmentation function. And so this kind of measurement we did. This is from Miguel Arratia's group. They did a projection for the yellow report, showing that we should be able to measure again the Sivers function with relatively high accuracy here. And then kind of a corollary to that, if we look at, say, hadrons within the jet, so this is something that we do at RIC, of course. STAR has released several papers looking at asymmetries based on the position of the hadrons within the jet. We can do the same thing at the EIC. And again, like with the Sivers, we can isolate just the fragmentation function part without convoluting it with the PDF. And here again, we see some projections of the statistical power we can expect, along with some of the current knowledge of these of the Collins fragmentation function. And so, of course, here from a detector point of view, you really want good PID to isolate your pions. You can also do this measurement for kaons and protons, etc. So those two measurements we can also do in charged current. So that was what I showed was for neutral current. We can do the same thing in charged current, where instead of looking at the jet with respect to the outgoing electron, you look at the outgoing neutrino, which you reconstruct from missing energy. So of course, this places quite stringent constraints on the hermeticity of your detector. So you can try to measure all of the transverse energy in the event, and then kind of see from that reconstruct where the neutrino must have been going. But again, just because of the nature of the charge current interaction, you're automatically getting some flavor separation. You're looking at predominantly one flavor of quark here, and actually. So if you extend that to look at hadrons in the jet, so they claim that this in this charge current process, the Collins asymmetries will be exactly zero because of the holistic structure of the interaction. So you can, of course, you can test that zero, and in the for the Sivers case, for example, you can look at a flavor separated sample. We can also look at the gluon Sivers TMD by looking at, again, these dijet correlations. So again, this photon gluon fusion process, which gives us access to the initial state gluon. So again, we look at modulations of the angle between the spin of the proton and the dijet system here. And you can do this using, of course, this was studied using dihadrons, charm, either, inclusive charm measurements or dijets. And it was found that dijets actually give you the best control and the best access to the underlying Sivers asymmetry. Again, and this is leveraging the fact that your jet proxies for the outgoing partons. So looking at the nucleus as a laboratory for QCD. So here we're talking about things like basically the bulk properties of cold nuclear matter, and using the jets as a probe to explore that state. So again, coming back to these lepton jet correlations, you can think about a series of measurements that kind of, I think they were referred to as tag and probe. So in somewhat analogous to say, a boson jet measurement in a heavy ion collision, where you look at, say, a photon jet correlation to learn about how the jet is modified as it goes through hot matter. You can look at the scattered lepton and then look at how the jet is modified as it moves through the nucleus. And of course, at the EIC, where we have control over our kinematics, you have all kinds of knobs you can turn. Looking at different news, for example, to control the depth at which the parton starts showering either inside or outside the nucleus, different Q² X. So you can really map out in multiple dimensions what's going on with the matter in this system. Of course, as well, we can look at things like REA, ratios of REA, with different jet radii, which helps us reduce the impact from initial state nuclear PDFs. And so here we can see some predictions for what the modification should look like for various jet radii. And yeah, so you look at the number of jets in EA versus EP. And then you can form these ratios to isolate the final state effects. Finally, coming to understanding hadronization, both in the vacuum and the nuclear environment. So I think this is kind of the realm of jet substructure, really, where we can look at actually the energy patterns, the distribution of energy within a jet, the distribution of various quantum numbers, flavor, spin, charge. So you look at you look in detail how those things are distributed within the jet, and there's a whole host of observables that allow you to do this in a systematic way. I show here, for example, this so-called angularity. So this is basically a weighted sum of where the energy sits with respect to the jet axis. And actually, you can then you can compute this perturbatively and then convolute it with a shape function that tells you somewhat, that tells you about the soft physics that you're probing. So if you you can do this as a function of jet PT and this parameter A, which kind of shifts between. You can think of about it as shifting between some of the traditional substructure variables, such as mass and broadening and things like this. So you can actually map this out in some detail. You have control of whether you're in you go into or out of a regime where your perturbative corrections matter. And so then you can get a handle on this shape function, which is telling you something about how the non-perturbative aspects of your shower behave. You can also just looking individually at hadrons within the jet. So here we see a recent paper out where they proposed this what they call RC. It's basically a ratio of a charge ratio of the two leading hadrons within the jet. So you can look at, for example, charge correlations as a function of jet PT, or say formation time, which is telling you kind of when in the shower evolution these things occur. You can also look by looking at different species. You can look at the kind of the flavor distribution within the jet shower. And so in both of these here, you see comparisons between different Monte Carlos, which employ different hadronization models, Lund string or cluster hadronization. And so you can see there's some sensitivity to these differences for all of these observables. Okay, so I want to go just really quick through some of the kinematics. This might be a little bit basic, but I think it is useful to think in detail somewhat about just the kinematics that we're looking at to inform us, what kind of energies we should expect, where jets will live in our detector, and then what that implies for how we should design our detector and actually measure these things. So here we just see the standard XQ² plane for reference, and I show I'll be showing the highest energy and the lowest energy we plan for at RIC, 18 on 275, 5 on 41, and you kind of see where those regions, the regions of phase space we can explore with those energies for different Y values. And so here we see kind of a schematic of the detector. So if we're looking at hadrons, generally, if you're looking at hadrons in the forward direction, you're probing high X. If you're looking in the back, and then of course where your scattered lepton sits, your event kinematics, X and Q squared. So generally, when we're at low Y, we're probing the higher X region, and these jets are going to be sitting at positive pseudo-rapidity, whereas for high Y, we're going to be at low X, and our jets are going to be at negative rapidity. We'll see a number of these type of plots. So this is for 5 on 41 beam energy. We're going to look, this left-hand side here is looking at a low Q² region. This is looking at a high Q² region, and the different panels are progressing through Y. So going from low Y to high Y. And you can see the distribution of the struck quark and the scattered electron, and you can see how that evolves as you move through Y. So as you go from low Y, your quark sits in this positive pseudo-rapidity region, and then as you progress through, it moves up into the backward region until it's taking roughly the beam energy. And so you see as you go to higher Q², everything kind of shifts to higher pseudo-rapidity. And then if we see how things evolve in energy, you can kind of just go back and forth, and you can see as we go higher in energy, everything kind of again now shifts back to the more negative region. Of course, here I show just the struck quark. Of course, there's going to be, once you add in things like final state radiation, this is going to smear out where this parton sits in your detector somewhat, but the same general features are still seen. And then once we move on to, now this is a plot showing the distribution of charged particles within the detector. Here I show charged particles, but things like neutrons and gammas follow roughly the same same pattern. And so now we kind of see that the features that were evident at the partonic level are kind of spread out. Generally you do see particles that are associated, of course, with the struck quark, but now you also see a host of other particles kind of filling the kinematic phase space. And so then the question is, how do we go from this, the particles that we can actually detect, back to the partons that we want to see? And of course, we do that via jets. But before I show that, I just want to quickly mention this XF variable, X Feynman. So in some sense, this is showing you how correlated a certain particle is with the parton that was struck. And so positive XF are particles that are more associated with that parton, and negative XF are particles that are not associated. And so by studying particles or jets that live in these different regions, we can look at fragmentation in the current in the target region and look for differences there. And so an interesting thing here, when we go to lower energies, 5 on 41, these actually these kind of target remnant particles come more into our detector acceptance, where at higher energies they're kind of outside of. I should have mentioned these red lines kind of represent the ±4 in pseudo rapidity that our central detector will roughly cover. So a quick note on jet algorithms. Of course, KT or in some cases KT. You can ask if these and, for example, the bright frame, where by definition your jet PT is very low because it's defined to be along the z-axis, and you can consider using different measures, such as a spherically invariant measure kind of designed for something like electron-electron collisions, or there was this new class of measures out called Centauro, where basically you can see here, this is a picture of how partons are clustered into jets in the bright frame, and as you see, as you move to the poles here, you kind of get a pathological separation of jets. So basically all these partons that are associated with each other are actually clustered into different jets. But if you move to something like a Centauro or a spherically invariant measure, they actually are all associated with the jet a single jet, as they should be. So you can look at the distribution of jets again. Now, this is for anti-KT again. So they roughly follow the same kind of shape from the particle distributions that we expected. We can look as well at EEKT, the spherically invariant measure, and we see we start populating more these forward and backward regions, as you might expect from the behavior of the clustering itself. And so one way, maybe the so here, if the parton just in eta phi space, and then look at the correlation between the parton energy and the jet energy, and we see jets, we do a pretty good job, but as we move towards to the lower, actually, if we move to EEKT, see that the EK algorithm does a better job reconstructing the kinematics of the jet or of the parton. So just very briefly, again, here is a conceptual model of the detector. This figure is a little out of date, but all of the major features are still here. So for jet measurements, the tracking is going to probably be the most important component here. Roughly 2/3 of the energy of the jet is contained in charged particles. And these charged hadrons are of low enough energy that measurements in like say a hadronic calorimeter are going to be rather inaccurate. So things like tracking and PID are going to be very important. But of course, we also have full calorimetric coverage, both electromagnetic and hadronic. And yeah, I mentioned PID being important. We have full coverage there as well. I don't have a lot of time left, but I want to briefly mention, are we done? Okay. So just real briefly going through the fact that the EIC is going to be the first machine with a major crossing angle. I guess actually as a historical anecdote, the first collider at CERN had something like a 15-degree crossing angle, but but the first modern collider and detector with a significant crossing angle of 25 to 35 milliradian, depending on which interaction region you're at. And that, of course, is going to have consequences for what we measure. And so basically, now because of this, we don't have a unique, we no longer have a unique z-axis anymore. So just to reduce synchrotron radiation, the detector has to be aligned with the lepton beam. But of course, in some sense, especially for forward jets, your physics is following the hadron beam. So if you measure distributions with respect to the lepton axis, you get these features, this hot spot in eta and phi. Where basically your beam is going through your detector. So you can consider, you want to correct for this before you start clustering your jets. So you can consider just doing a coordinate transformation and measuring things with respect to the hadron beam axis, which again gets rid of this hot spot. But now because we don't have a unique axis, if you want to do correlations between something in the forward direction and the backward direction, you're actually distorting your backwards region. And so a more intelligent way to do this would be just to boost into a head-on frame where this crossing angle, this relative angle between the beams no longer exists. And so you can do this boost and rotation to get you into a frame with roughly the same energies as before, but now a common axis. And of course, this transformation basically reproduces the effect that you'd see without any crossing angle at all, as we expect. Just a quick word on acceptances here. So what I showed before, I assume that I can detect all particles that are thrown out. Cut matters a little bit. Basically, you want to cut, instead of cutting along the electron beam, you want to cut basically on a fiducial volume centered around the proton beam, and so doing that again kind of then alleviates this bump that you see. I'm sorry, I'm really rushing through this, but basically we can place our cuts and define a frame in which we don't have to worry about these crossing angle effects. We just have to do it carefully, and that has some implications for the detector. So basically, one of the things that we're looking into is doing an insert in the forward calorimetry region that really follows this beam pipe and allows you to place your fiducial cuts as close to the beam pipe as you can. And so since I'm grossly over time, I think I just skip some future directions and move to my summary, which I'll just post and look. Yeah, it's kind of coming in and out. All right. Working? Yeah. I think so. Yeah. All right. Okay.
May I
Getting the
go
thumbs up.
with my question? Okay, Brian, may you go please to your slide 21? Yeah. So in this process, so you cannot measure the neutrino. So how do you reconstruct the neutrino again?
So basically, it's a missing transverse momentum or missing transverse energy measurement where you take advantage of the hermeticity of the detector. You measure, you basically measure all your transverse energy, and you see where you're missing.
So you have to measure all the particles in the jet?
All the particles in the event.
In the events,
Yeah.
yes.
And so, of course, I mean, of course, this is...
that we need? Which is the resolution that you need?
Yeah, so I mean, I didn't post here, but of course, the paper this come from, they do, a lot of work showing, how well you can reconstruct things, and these are, the precisions that they're showing all assume, this was done in a fast simulation model, but assuming somewhat realistic properties for the various detectors that we'll have. So, the calorimeter resolutions we can expect, the tracking resolutions we can expect, the fiducial coverage. So what we're assuming will be sufficient to do the measurement that's shown here.
And may I have time for another question about the jet? So in the jet, your leading pion, what is the Z of your leading pion?
So for these measurements,
well,
or just for anything?
Yes.
Well, it varies, right? I mean, I think.
But do you have a cut on below which you cannot consider as a leading particle for the jet?
So I think generally, leading particle is always a little ambiguous, but yeah. So I mean, I don't remember what the mean Z or the mean Z value is. Probably peaks at something like 0.2 or 0.3, but it's, you can look at the full spectrum. So if you want to look at high Z particles in the jet, you can select, you just select that part of the spectrum, and of course we should have enough statistics.
Because I'm trying to understand if you have, for instance, a quite uniform distribution in Z of your particle. So how do you define the direction, and how do you choose the quark that indeed has the PT that you want to measure, or the Sieverts effect for this quark? So
yeah,
so
I
think
think
Z is relevant variables, right? Otherwise, how you can be sure that is the quark that?
I will give to okay.
So I mean, I think in some sense the clustering itself is what associates your entire jet with the parton, and then of course if you want to select a sample of jets, where you have one high Z particle, you can do that.
So you don't use C in the same way as in CDs. You reconstruct the jet energy, and then you take the PT of the jet, and you take the PT of your hadron inside the jet, and that ratio is your C. And you get a uniform distribution. You can look to all the RIG papers, which we have already done on hadron in jet and LHC. It depends mainly what C you can reach, depends on the lower cutoff of the hadron in your jet. And in general, we use 200 MeV or 300 MeV, and then it is your jet spectrum. Of course, you can have jets with 10 GeV, you can have jets with 50 GeV, and then 200 MeV to that gives you that. And you look actually to all of the hadrons. You don't use a leading, because this concept of leading hadron means in principle nothing. Yeah. Yeah. So what you, Brian, if you go back to the paper which we did on the sievers, remember with the jets, there actually it's not only the PT, you also need to measure the JT of the hadron inside the jet, which means you have the jet axis, and then you look to the PT with respect to the jet axis, and that actually then gives you nicely the sievers function, and you average over all your hadrons inside the jet. Like in CDs as well, you cannot say it is just this one. If you have 5 hadrons, you bin every single one in a bin in JT, C, and the PT of the jet.
Yeah.
Doesn't work?
Well, I don't, yeah, it's, yeah. Oh, that one, yeah.
Any more questions? Okay, one more question.
You showed the double spin symmetry, ALL, and there was a big jump from next to leading order to next to next to. Do you know what happened? Yes, so the magenta versus bluish. Do you know what happens there?
I don't know.
Unfair question, but I'm just, some new diagram, something new, or?
Yeah, I don't remember in detail what the explanation for this difference here at larger eta is.
Okay.
Yeah, I'm sorry.
The reference is there. Okay, thanks.
Yeah.
So, okay, so now we have to thank our colleague. We go to our next presentation by Cédric Lorset.
I don't know if you want the clip on. You don't have it here, so.
Okay, so now we have Cédric Lorset talking to us about relativistic spatial distribution of charge and magnetization.
Okay, good morning, and thank you very much for the organizers for inviting me here. So we talk about the relativistic spatial distributions of charge and magnetization. So we have already heard many times in this meeting that, well, we want to measure different quantities like GPDs, form factors, and other things. And then for some of them, we need the Fourier transform to have kind of interpretation in space. And so what I wanted to do with this series of work is to understand better under what condition this makes sense, and also to see whether we can understand the frame dependence, because people have proposed different frames with different Fourier transforms, and we get totally different pictures. So I try to have a global picture that allows you to essentially connect a different picture and see that they are not inconsistent, but they just reflect different aspects. This is the outline. So just a brief reminder of the process of elastic scattering. So I will be focusing essentially on the electromagnetic currents, but the goal is really to apply it to the energy momentum tensor because you can, in principle, access the gravitational form factors through the measurement of GPDs. And if you know this, you have the gravitational form factors, you can learn about how energy, angular momentum, pressure forces are distributed inside the system. So you learn much more about the structure of the hadron. That's what we are after. And so I will do the basic set of interpretation that have been proposed for the electromagnetic form factors. And I will present a new way to look at things, which we call the phase space formalism, and study in detail the frame dependence on the picture that you can get. And then discuss in particular the notion of electric and magnetic polarization that hasn't been much developed in our field so far. Okay, just starting with something that you know very well. So classically, if you, for example, shine some plane wave on a crystal, the traditional explanation is that each of the ions here electrons in the ion start to oscillate with the same frequency as the initial wave, and each side becomes a source of a secondary wave. And then if you look far away, all this secondary source, all the plane waves, all the spherical waves looks like essentially plane waves far away, and they interfere with each other. And what you measure is the result of that, so you get essentially figures like this, so diffraction pattern, where the intensity of light gives you essentially the square of the amplitude, of the wave amplitude. And to understand the physics of that, essentially, the amplitude is just a superposition of the plane wave associated with each scatter distribution. So that's basically the origin of why we think that Fourier transform of form factors is the charge distribution and vice versa. So you can apply this kind of idea to different systems. So essentially, you can do this with crystal atoms. We have a typical size of 10 to the minus 10 meters. And you can basically use essentially X-rays because that gives you the right size, so the right scale. But if you apply the same idea to nuclei and nucleons, well, it's harder. You need much higher energy, so it's very complicated. And so instead of using electromagnetic waves, we start with electron beams, and we use then the virtual photon to probe the internal structure of the nucleon. And also one point that is important to realize that in this picture, we completely neglect the recall of the ions. And this is justified because you are in a lattice, and each ions also behave collectively. So essentially, the inertia of the whole system is super large, and you can neglect the recoil. But in the case of, if you look at the internal structure of nuclei and nucleons, you involve energy which are of the same order of magnitude as the mass of the system, the inertia of the system. So you cannot neglect the recoil. And this affects, of course, your picture and also makes all the things complicated and interesting. Okay, so for the relativistic treatment, basically what you do, so you look at the scattering process like this one, so elastic scattering. You do not excite the nucleon, you just deflect it, you do not break it, and you measure the differential cross-section, and you compare with what you expect for a point-like target. And the difference, or the ratio, essentially is encoded in Lorentz invariant function that we call form factors. And in the case of spin-zero targets, you just have one single function, and that was really the original idea and proposal by Rosenbluth in these famous papers. And if you go to higher spin target, for example, for a nucleon, then you need two form factors, so the electric form factor and the magnetic form factor. So typically, Q squared is the virtuality of the photon here, squared. A convenient dimensionless combination is Q squared divided by 4 times the mass of the target, and then you have something that's related to polarization. So that's basically what you do. You measure this, and then you try to extract the electromagnetic form factors. And we have plenty of data, so there are much more data than you can see here. Just here, a selection of data, experimental data that are compared with recent lattice results that you find in this paper, just to have an idea of how they compare pretty well. There's still some improvement to be made, but still we have a pretty good, reasonable agreement. So we know pretty well the electromagnetic form factors. So the question is, what is the physics that you can learn from these electromagnetic form factors? So first, we need to have the field theoretic definition of the electromagnetic form factor. So essentially, it's an invariant function that describes the interaction of the photon with an external target, which can have internal structure. So it encodes all the internal structure, and based on Poincare symmetry, if you look at the matrix elements here, well, you are forced to consider, so the initial nucleon and the final nucleon are essentially 3 spin 1/2 particles, so you describe them with Dirac spinors, and then you have to insert essentially a matrix in Dirac space. And with Poincare symmetry, using the fact that you see the current must be conserved, you have discrete space-time symmetries, you have only a finite set of structure that you can, or tensor structure that you can use, and the traditional ones are these ones. So essentially you take the gamma mu, so the original thing that you get in the Dirac theory, you multiply by a function, which basically gives you how the charge should be spatially distributed. And then you have an additional contribution that would account for the fact that you have also magnetization effect that can be different from the Dirac theory. And the normalization of these functions, so at q squared equal to 0, gives you the total charge and the anomalous magnetic moments. And the form factors that I mentioned before, GE and GM, are particular linear combination of these, which are convenient for the description of the cross sections. Okay, so how is it justified to consider the Fourier transform in the non-relativistic case? So in the non-relativistic case, we can definitely define position eigenstates and look, for example, at the density operator sandwiched between position eigenstates. So you can represent the position eigenstate in terms of momentum eigenstate through Fourier transform. You switch your coordinates to the average of 3 momentum and the 3 momentum transfer, and you get such a matrix element. And a key point here is Galilean symmetry. If you're in a non-relativistic theory, you have a Galilean symmetry, and Galilean symmetry ensures that if you look at the matrix element in momentum space for your density operator, well, it doesn't depend on the average momentum of the nucleon. That's really a key feature. And by doing so, thanks to this kind of symmetry, you can perform the integration over the average 3 momentum. So you just have an exponential here that gives you a delta function. So you get a transition that is diagonal in position space, and then the rest, which is just a Fourier transform with respect to the 3 momentum transfer, is what we call the internal distribution. Of course, position eigenstates are not physical states, they are not normalizable, so you should consider wave packets. So you can consider a generic wave packet properly normalized. And if you are interested in the charge distribution in a particular wave packet, well, you just have to consider the convolution of the wave packet in position space with the internal distribution. And that's really the basis of the probabilistic interpretation. You have an internal distribution, and then you fold it with the probability that the system is at position X in space. So everything is clear here. Things get more complicated in the relativistic regime. So in the relativistic regime, we start, for example, with, again, the wave packet. Here we consider a generic operator, but think, for example, about the charge operator here. You can still represent in momentum space with a wave packet here. For convenience, I will work with the non-covariant normalization for the state, but you can rephrase everything in terms with the covariant one. It doesn't change anything, just for convenience here. Okay, and usually people make a crucial assumption, which is essentially they say, okay, let's consider that the wave packet in momentum space doesn't depend much about, well, it's pretty flat. So you can essentially approximate the wave packet at p plus or minus momentum transfer as the wave packet at the average value of p. By doing so, again, you separate the p from the delta dependence, and you would then again interpret this Fourier transform as the internal distribution. So it's basically what you can find here. Of course, there are limitations for doing such a thing. Very importantly, if you consider a system with a size d, if you want to find the internal structure, you need sufficient resolution. So you need that the momentum transfer should be sufficiently large so that you can really probe the internal structure of the system. And you want also that the momentum transfer should be much smaller than the width of the wave packet. And also you want everything to be smaller than essentially the mass or the inertia of the system that gives you essentially the Compton wavelengths. So if you look at the hydrogen atom, things are fine. So if you look at the ratio mass of the hydrogen atom times its size, you get essentially a window where the approximation is valid, which is a range of 10 to the power 10 to the 5. So we are safe when we do this kind of reasoning for the hydrogen atom. But for the nucleon, it's not correct. We have a very narrow window where this is truly justified. Nevertheless, what Zaks proposed is say, okay, let's consider which is centered around p equal to 0. So essentially you look at the system which in average is at rest. In that case, the inertia of the system is simply its mass, and you replace the square of the momentum space wave packet, I should have a tilde here, with just a delta here. You see an inconsistency here, because first you assume that you have a very flat wave packet in momentum space, and then you take a limit where it's super narrow. So it cannot work really. Anyway, he did that, and then proposed to look at the amplitudes in the bright frame. So the bright frame is defined by a frame where the average stream momentum is 0, which you interpret as the average rest frame of the system. Or if you wish, the initial momentum is exactly opposite to the final momentum of your system in the scattering. And in such configuration, you have no energy transfer to the system. So essentially, you get a distribution that doesn't depend on time. This would be a static distribution. And if you do the exercise, you compute the amplitude in the bright frame, well, you get very simple results and not that surprising, because the spin structure that you get for the density and the current, the charge current, exactly the same structure as you would get in non-relativistic limit. So you have a clear connection with the non-relativistic theory. And if you consider any other frame, well, things will be more complicated. You will have unpolarized and then a spin-dependent contribution here. And for the current, we'll have also a combination of spin-dependent and spin-independent contributions. So the bright frame is really special in the sense that it makes the spin structure the simplest you can get. And then, okay, let's do then a three-dimensional Fourier transform. And you get essentially the usual definition of the charge density in the bright frame according to Zaks. So if you look at the original papers, first Zaks had this 1 over square root of 1 plus tau that was mentioned yesterday. It's essentially that if you look at the inertia in the bright frame, since the initial and the final particle are not at rest, it's only the average momentum, which is 0. P0 is not the mass, but it's mass times this kind of relativistic factor. And conventionally, if you look at atomic physics, nuclear physics, and people like to make non-relativistic, semi-relativistic expansion and define what they consider as internal contribution and external contribution, and by definition, they chose to remove that factor. But it's something that you do by hand. It's not something that is consistent with relativity, etc. If you look really at how the Fourier current should transform under a Lorentz transformation, you realize that in principle, you should keep the factor over there. It has been stressed in different places, but unfortunately, it wasn't really considered. And probably the reason is because we knew already that there was some problem with the probabilistic interpretations. Probabilistic interpretation up to some relativistic corrections. Since we do not really know what those relativistic corrections are, well, people can argue that, okay, just forget about that factor. But you have to keep in mind, this is purely conventional. If you do things covariantly, then you will realize that the natural definition is the one with the square root. So if you use the experimental data and then fit to the experimental data, and then the Fourier transform, that's basically the curves that you get for the proton, for example. So the conventional Zaks distribution would be just the Fourier transform of the electric form factor, so you get the red curve. And if you include this relativistic factor correction, well, it doesn't change the qualitative picture. You get something that you expect, essentially a lump of positive charge, and then it goes smoothly to 0. You can compare with the same distribution in nuclei, and what you observe is that the larger the nucleus, essentially you get a constant density. It's only at the edge that you get a smooth transition to a kind of skin or diffuse distribution to 0. If you go to smaller ions, or smaller nuclei, then you get, essentially, you lose this plateau, and you just have the transition just like you get for the proton. Now comes the neutron. The neutron will be very interesting in this talk, as we will see. For the neutron, what you obtain when you do the Fourier transform with or without this relativistic correction, you get exactly the same qualitative picture. You get a positive center, and then an outer region that is negative. How can we understand it physically or intuitively? Well, if you look at a neutron, the neutron can fluctuate in different states, and then Tommy Thomas can also talk a lot about it. You have many excitations that are possible, but the one that is possible one is that actually the neutron fluctuates into a proton and a pion. And the pion must be negatively charged so that the total system is neutral. And the proton is much more massive than the pion. So we expect that the proton essentially stays closer to the center of mass, while the pion, negative pion, goes at the periphery. And indeed, that's what you get. Positive inner core with a negative outer region. So everything seems fine. Now, if you're really worried about, okay, what are the relativity corrections? People have used different models, and nobody agreed on how to correct for those relativistic effects and recoil corrections. So another strategy that was proposed was, for example, to look in a frame where the inertia of the system is infinite. If the inertia of the system is infinite, you don't have any recoil correction, and a frame where the inertia is infinite is the infinite momentum frame. And in that frame, essentially, you have the proton that moves along, let's say, the z direction, and then you have a relatively small transverse momentum that is transferred to the system, but it doesn't change, it doesn't make the system recoil. And in that case, so you can also calculate the matrix element in the infinite momentum frame. As you see, for the charge density, now you have two structures, spin-independent one and a spin-dependent one. The structure is a little bit more complicated, but the nice thing here is that you don't have any problem with relativistic recoil. And you can even show that you will have no relativistic correction to it. It's exact from the relativistic point of view. You will have a strict density interpretation, and if you do the Fourier transform, well, you get two contributions. And I recently discovered that the very first people that proposed this kind of idea was already in the 71. It's a paper that is absolutely not known, so it made my day when I discovered that paper. Otherwise, it was these kind of ideas essentially reappeared about 20 years ago. So the infinite momentum frame is just one way to get to those relativistically correct density of charge, etc. But there are different approaches that lead to the same results. So one of them has been mentioned several times, the light front coordinates. So you do not need to go to the infinite momentum frame, but there are many aspects that is essentially the same as looking at the system that moves with the speed of light. Instead, you can say, I take the system at rest, and I take an observer that moves with the speed of light. You get exactly the same picture. More recently, people also considered kind of infinite momentum frame, and then you average over all directions such that you don't have not only a 2D distribution, but you combine 2D distribution in all directions so that you reconstruct a 3D distributions. I won't go into much detail here. So what kind of picture do you get with those light front densities? So for the proton, if you look at, so that's the transverse plane, so the proton is moving towards you with the speed of light, if you wish. Then you get essentially a lump, so nothing surprising. If you polarize transversely, you get a shift, as I already mentioned yesterday in Adam's talk. But things are more dramatic in the neutron case. That made kind of a sensation in 2007 when Jerry Miller did it for the neutron. And he realized that with the light front picture, you get a negative charge in the center of the neutron. And for years, several people have tried to find a way, a picture, a mechanism that would explain why we get a negative center in the light front charge distribution. And they failed. And the other thing is that if you polarize transversely, since the total charge is 0, you clearly see a dipole structure, which is also the reason why you have a shift here. So we have kind of a clear understanding of why we have a shift here. So things have already been mentioned yesterday in Adam's talk. You can see it from different perspectives. It's essentially the same physics. So I can consider, for example, a neutron at rest, and then I looked at the neutron by sitting on a photon that hits the neutron. Since from the perspective of the photon, I'm not measuring the zero component at rest, but a linear combination of the zero component at rest and the longitudinal current at rest, if my system has some orbital angular momentum, I can have an asymmetry, up-down asymmetry, because charge are moving inside the system at rest. And this match with, at least qualitatively, with the dipole picture and also the sign. And this can be understood also from a different perspective, saying that if you do remember how electric and magnetic field transform under a Lorentz transformation, if you start with 0 electric field in the rest frame and only magnetic field, in a boosted frame, you have an induced electric field. And the same if you have magnetic dipole moment in the rest frame. If you look from a moving frame, you will have an induced electric dipole moment. That's exactly what you see here. So this physics is clear. There's another piece of physics where we have less intuition, is the Wigner rotation that was already also mentioned yesterday. So we have no ambiguity about what we mean by spin for a system at rest. The problem is that also we have to define what we mean the polarization or the spin projection for a system that is moving. So there is some convention to define this. And the usual one is, okay, you have to define a boost, so canonical boost, so the usual definition for the polarization that you have for the free Dirac equation and so on. So you just take the rest frame and then you boost with a pure boost to a certain momentum. For example, the momentum in the bright frame, the momentum in the infinite momentum frame. And then you say, okay, the state will have the same polarization than the one at rest. What happens is that, and that's really a consequence of the Lorentz symmetry, is that boosts do not commute. That's really the crucial aspect. It's different from Galilean symmetry. Boosts do not commute, and the difference is essentially a rotation. So if you start from the bright frame, and then you boost to the infinite momentum frame, what you get is the infinite momentum frame state, but which is rotated in spin space. And this rotation is called a Melosh-Wigner rotation. You would get exactly the same phenomenon if you stay at rest, but you use the instant form polarization versus the light front polarization. In that case, you call it a Melosh rotation. But that's exactly the same physics. So if you work with the bright frame polarization, so the amplitude will be described as GE and GM. If you look at the infinite momentum frame, you would say, oh, I would use F1 and F2. So the question is, which set is the more physical one? So really the fundamental problems we have here is that we are after a spatial distribution. So intrinsically, what we mean by a spatial distribution is that we have first to fix a notion of simultaneity. So we have to choose a certain frame, and within that frame, you can say, okay, I have such a spatial distribution. If you change frame, you change your notion of simultaneity, and things get more, of course, more complicated. And really a key point is that if you really insist on having a probabilistic interpretation, you can achieve that only if you have Galilean symmetry. You need that, and this is achieved especially if the inertia of the system doesn't depend on the momentum. And so that works for Galilean symmetry, it doesn't work for Lorentz symmetry. You cannot have both at the same time. So the traditional perspective is the following. So people like to maintain strict probabilistic interpretation, and to get around with the problem associated with the recoil effect, well, either you neglect them, you invoke, for example, large NC, and then you say, I have an infinitely heavy target, so you can neglect them, or you go to infinite momentum frame where, because of relativity, your inertia becomes infinite and you don't have any recoil effects. I propose a different perspective, which is, okay, let's relax the pure probabilistic interpretation and use the full relativistic picture, essentially, that my density is a frame-dependent concept. I do not want to be stuck with one single frame. I want to be able to change from frame to frames so that I can compare what happens in the bright frame with what happens in the infinite momentum frames. And in certain cases, I can recover, in special cases, the probabilistic interpretation, but with a quasi-probabilistic interpretation, I have something which is much more general. So it's essentially kind of similar idea. If you have GPDs on one side, you have TMDs on the other side. With Wigner distribution, you can get everything all together in a single picture. Here's kind of the same picture with a phase-space approach. So you demand to localize your system not only in position or momentum space, but you want the system to be localized with average momentum P and average position R. So you need a phase-space picture. So in the phase-space picture, again, your matrix element you can represent as a phase-space overlap or integral of a phase-space density that we call a Wigner distribution, which contains all the information about the wave packet, and then a matrix element, which you can interpret as the internal distribution for a state that is localized in average position R, in average position P. Of course, because of Heisenberg uncertainty relation, you cannot have, in general, a probabilistic interpretation, but you have a notion of quasi-probabilistic interpretation. So that's the best compromise you can have between a pure position space picture, a pure momentum space picture. Is the phase space picture has both. And what happens is that instead of working with quantities as positive definite, you work with quantities that are still real, but they can be positive and negative. And usually the regions where they are negative, they are about of the order of h bar. And if you project this Wigner distribution either integrating over position or momentum, you get strict density in position or momentum space. But you get both picture or both information over there. So what we are then interested in is the internal distribution for a state that is localized at position R and momentum P. And I can use translation invariance to say, okay, I can set the system at the origin. And what I'm only interested in is the relative position with respect to the center of the system. And what we require here is that I will work in a subclass of frames, essentially the frames where I do not give any energy to the system. So we call them elastic frames. And this is a generic class of frames which contain the bright frame as a special case, the infinite momentum frame as a special case, and then you have all the intermediate case over here. And so by changing the value of P here, I can smoothly go from the bright frame to the infinite momentum frame. And with that, I can have an idea of why things are changing and understand how it's changed continuously. So for the elastic frame, as I mentioned, we will require that the energy transfer is 0. So for simplicity, since I have a non-zero momentum in general for my nucleon, I can choose the axis such that the momentum is along the z direction. I'm always free to do so. And so if I want zero energy transfer, I need 0 momentum transfer in the longitudinal direction, which means it amounts to integrated over the longitudinal direction. So I basically lose the longitudinal information. I just have information about the transverse space. But OK, that's the way it is. You have always to pay a price. There's no free lunch. And so you can define a 2D charge distribution for any value of pz. And just by just a Fourier transform, you just have to compute the amplitude in the elastic frame. If you go to the frame where pz is equal to 0, well, it's just the projection in the transverse plane of the 3D distribution. Nice connection. If you go to the infinite momentum frame, you get, or the pz going to infinity, you recover the infinite momentum frame distribution. It's a nice interpolating object. So, so let's then compute those matrix elements in the elastic frame. So remember that we have parameterized in terms of form factors F1 and F2. We have said that G and GM were linear combination of F1 and F2. And if you play a little bit with the Dirac equation, equations of motion, and so on, then you realize that you can also find a parameterization directly in terms of G and GM. It's not that complicated. It's a little bit more complicated than F1, F2, but this is fine. And the nice thing is that with the train I, then you see that this term has no spin dependence. It's proportional to the form momentum of the particle, so it should be proportional to the form velocity of the particle. So it's natural to think that, oh, that should be a convection contribution to the current. While the other one involves gamma lambda gamma 5, so it has to do with spin. And then you have a cross product with the momentum transfer. So essentially, this is a momentum space version of the curl. And so the second term could probably be related to magnetization. So with this GE-GM decomposition, you have a nice matching with convection plus polarization contribution to the current. You compute, for example, the charge density in the elastic frame, then you can separate the convection part and the magnetization part, while you get things, just something is proportional to GE and GM with some momentum-dependent factors. And if you go to the bright frame, you recover the expression in the bright frame, you go to the infinite momentum frame, you get the linear combination of G and GM that gives you F1. So everything is consistent. So to see things in pictures, you do the 2D Fourier transform, and that's what you get. So if you're in the bright frame for the proton, what you get is the black curve over here, so just the lump. And if you increase the momentum, essentially the charge distribution becomes more and more concentrated around the center. And the reason is because you have two contributions. So the first contribution is the convection contribution, so it doesn't change much, you see. And what happens is that as you increase the momentum, you have a contribution from the magnetization distribution. You combine J0 with J3, and because of the spin rotation, you have also a contribution to the spin-independent contribution. So you get an increase in the center due to the magnetization. And this explains why in the neutron, you get a negative charge distribution in the center, because in the bright frame, you have what you expect, positive charge in the center, negative charge at the periphery. But as you increase the momentum, you start to mix an induced magnetization contribution, which is negative because the magnetic dipole moment, the magnetic moment of the neutron is negative. And at some point, this contribution is much larger than the convection contribution and creates a negative, apparent negative distribution in the center of the neutron. So what this kind of suggests is that there is no, intrinsically, there is no negative lump of electric charge inside the neutron. It's just something that you would say if you look at things from the infinite momentum frame, or a frame where the nucleon is moving with the speed of light, but not if you look at the system when it is at rest, let's say in the bright frame. Do the same thing with transversely polarized target, and then you increase the momentum, so you have something that is spherically symmetric, and then it shifts upwards. And for the neutron, you see clearly the dipole that appears over there. Okay, thanks. So usually people focus on the charge distribution, but the charge distribution is just one aspect of the electromagnetic current. You can also look at the momentum or the current distributions. And if you want to connect the matrix element in a generic frame to the matrix element in the bright frame, well, the formula is known for a long time. You have not only a mixing of the Lorentz components, but you have also the spin rotations, the Wigner spin rotation. And that's really what we have no intuition for. And that's really the crucial part that makes the complicated distortion of the picture when you change from one frame to another frame. If you work with a spin zero target, you don't have those spin rotations, and everything is consistent if you work with light fronts, infinite momentum frame, or bright frame. It's the same picture. As soon as you have spin, you have the spin rotation, and this changes the apparent picture or the spatial distribution. And to show that this formula is indeed correct, well, we computed explicitly the left-hand side with the ordinary Dirac spinors and try to put things in a form that would be consistent with that. So express everything in terms of the bright frame amplitudes, which are on the right-hand side over here. And you have indeed something where you combine the zero and the third component. So the zero and the third component, you have PZ over P0. And then you have the spin rotation that's essentially affects the spin density matrices here. So you have a rotation that's explicit here. And we can even determine the angle of rotation as a function of the momentum of the nucleon, which is given by this combination. And it is the same, of course, for spin 1/2, spin 1, any spin. It doesn't depend on the value of the spin. So we can get the charge distribution the charge distribution for transversely polarized targets, the longitudinal current, transverse current. I won't spend much time here. I will go to the last part of the talk. So since we have a clear, in a sense, separation between convection contribution and polarization contribution, we propose to look at the notion of polarization, so magnetization density and electric polarization density. So it's something that is well known in the classical theory, where basically people like to, if you look at electromagnetism in a medium, in a relativistic way, you will decompose your electromagnetic current into two contributions, the convection current that will be proportional to the force velocity of your particles, and then a polarization current that is due to the fact that either the particles have spin or they are orbiting around a center, which is, for example, the nuclei and this kind of stuff. And if you look at the charge density, well, you have a contribution from the convection and the divergence of the polarization, the electric polarization. If you look at the current, you have more contributions. So just like you can combine electric field and magnetic field in a rank 2 tensor, you can combine the electric and magnetic polarization into a rank 2 tensor. This is the magnetization polarization tensor, which is here. And so we can try to match this kind of decomposition with our parametrization. So if you start with the standard usual one, well, it's not clear. You don't have any clear convection current. While if you use this one directly in terms of G and GM, well, this suggests, since this is really a curl in the 4-dimensional form, that this combination or this structure should be the definition of polarization for a spin 1/2 particle. It's actually not the only possibility. Another possibility is this one. You can use the Gordon decomposition to re-express this like this. So you will have now F1 that is multiplied by P, so this is really convection current. And then you have another spin-dependent contribution that is proportional to GM. So in any case, you will always have something that is proportional to GM. The only difference is the tensor structure that you get in front. So you have some kind of ambiguity. So to lift some of this ambiguity, we can look at what happens in particular frames, and I hope I have kind of motivated the fact that the bright frame is the most natural frame if you want to interpret in terms of internal densities of a system at rest. You can use both representation or decomposition of the charge density. So if we use, essentially that one, you have no contribution from the polarization at rest. So in the bright frame, this term is 0 with this decomposition. And so all the charge distribution is purely convective. But if you use the other decomposition, so based on the Gordon decomposition, you will realize that you will have a convection contribution that is the red one, and then in green here, the polarization contribution. You have a non-zero polarization in the average rest frame of the system, and they go in opposite directions, and they cancel largely. This is not very natural, and then, to my mind, suggests that the correct definition of polarization is given by this tensor. So I will only focus on that one. So now that we have identified our polarization density, we can do all the play with the Fourier transform, etc. Let's start in the bright frame, so you get complicated expression. And you get here a genuine magnetization distribution. So again, the proton is moving towards you. I polarize my nucleon in the transverse direction, and I have a magnetization density that is essentially pointing parallel to the proton spin. And if I integrate over the space here, I get the total magnetic dipole moment of my nucleon. In the literature, people like to use other definition for densities or with magnetization. They like to define, for example, effective magnetic density. So even though magnetic monopoles do not, we haven't observed yet magnetic monopoles, we can define effective magnetic monopole distribution, and then define an effective magnetic dipole moment as the magnetic charge distribution multiplied by the position vector r. And then you get, with the same data, but with this transformation, this kind of distribution. So sometimes people will call this the magnetization distribution. I will not agree with that. If I look really at the formula, I would say each arrow here corresponds to the contribution to the magnetic dipole sitting at the origin, because it's r with respect to the origin, given or originating from the effective charge, effective magnetic density at the points away from the center. So it's a little bit different. And the other option is also to consider, for example, the circulation of current. So that's more classical picture where the magnetization is due to the circulation of electric charge. So you will consider R cross J, and J would be the curl of the magnetization. And then you get also another picture. But if you integrate all those three pictures, you always get the same total magnetic moment. But you see the interpretation in terms of spatial density is a bit different. So that was in the bright frame. You can look in an elastic frame, so you get something that is similar for proton-neutron. And you have now an induced polarization contribution, and you can even go to the infinite momentum frame where the distortion is a little bit larger. The last thing that I will focus here is essentially that, remember that we had a dipole shift of the distribution, or for the neutron, a clear dipole structure. So you can measure the magnitude of this induced electric dipole moment. And you realize that we'll have two contributions. You have a contribution that comes indeed from the fact that you have a magnetic dipole in the bright frame, and then you go to a boosted frame, and then you generate a electric dipole moment. So that's the first term. But you get an extra contribution, which is more complicated. It is due to the spin rotation. It has to do with the fact that we have defined all those densities with respect to the center of the target. But nobody says how the center of the target changed with the frame. We always assume that it's a physical point which transforms like a four vector. In reality, it's not the case. You have a shift that has been studied in the 40s, and you get exactly this momentum dependence. And if you go to the infinite momentum frame, the combination collapses to the usual F2, the anomalous magnetic moment. So this explains why in the infinite momentum frame you have the dipole, and why the magnitude is given by F2 and not GM. If you just do pure light fronts, you don't understand why it's F2 and not GM that appears. And you can generalize this to any spin. You get a generic formula, which is compatible with what you get in the light frame if you look at the infinite momentum frame. And the nice thing is that for point-like particle, you will have no electric dipole moment in the infinite momentum frame, and this amounts to having a geomagnetic ratio G equal to 2. So it's an interesting observation that's made before. Of course, if you have internal structure, G deviates from 2. So this brings me to the conclusion. So really the takeaway message is the following. So there's a clash, really, fundamental clash between a probabilistic picture and having the Lorentz group or Lorentz symmetry. So I propose to work in a phase-space approach. So I kind of relax the probabilistic interpretation. I only require a quasi-probabilistic interpretation. But with that, I can really consider any frames, and then I find a way to interpolate between the bright frame and infinite momentum frame and see how the different pictures are connected to each other. And why the pictures are different is essentially because you have spin rotations and something that we really are not familiar with. And if you really take into account this wing rotation, you can really see what happens gradually, how the distribution transform. And the result of those analysis points to the conclusion that actually it is the Zaks form factor that represents, in my mind, the best picture of a system at rest, rather than F1 and F2. Thank you very much.
Questions to Cédric? Okay.
Thank you for the nice talk. I have a very selfish question. So if you take the example I would have about using the bright frame to make calculations of form factors who come from the bag model, for example. So there's, I can think about one paper by Melnichuk and G and Song, and I also have one in which I don't boost anything because it was complex. So in that paper, they use some kind of boosted wave function. Is it similar to what you said is correction that you would have this square root of 1 plus, or equivalent somehow? And then how could you use, do you have an example in which you use bag model results from the bright frame to try to then interpolate to the other frame, the infinite momentum frame? Or is there something that you can do to show simple results in the bag model to the other frame?
Okay, so if you calculate things in a model, so for example, you have some wave functions. Usually you truncate your Fock space, and then you say, okay, I know my particle content, and then when I boost to a different frames, I have two contributions. I have a kinematical relativistic effect, but I have also dynamical effects. And the complicated stuff are the dynamical effects. Here, since I analyze everything in terms of the form factors that are by themselves Lorentz invariant, and that's really the key issue when you do a calculation with wave function, to extract form factors that are Lorentz invariant. That's the point. All the effects for comparing the distribution in the bright frame to the infinite momentum frame here are purely kinematical.
So you do not apply this prescription, only if you had a consistent.
Yes, exactly. You need a fully consistent model for. That's the point. That's the problem. But you can measure the gravity, so the electromagnetic form factors. You can extract information about the gravitational form factors, and then you have interpretation that doesn't depend on how you define your model for the wave function or whatever. No, it's everything's encoded in form factors that are by definition construction Lorentz invariant, and the rest is purely kinematical effects. Not necessarily, because you have first to prove that the boost that they proposed is totally covariant. And usually it's effective up to some approximation, and that's the point.
Okay.
I just wanted to give a quick comment. One of the slides you said that it's clear in the infinite momentum frame that in light front coordinates why it is that F2 rather than GM is what gives you this induced or apparent electric dipole moment. In tilted coordinates, I think it's also clear that F2 is related to orbital motion, whereas the F1 part of GM is related to the intrinsic magnetic moment. And the distortions that you see in transversely polarized states in tilted coordinates should be related to optical effects due to orbital motion. So F2, I think, would encode orbital motion, and that's how it would be understood, as why it's there in tilted coordinates at least.
So if you use the tilted coordinates, and it would be, for that point, I think, the same for the light front coordinates, or if you're working with infinite momentum frame, you have to localize your system in position space, and the point that you define as the center of the system is not the center of gravity of the system, but it's the center of P+, which is shifted when away from the center of the target, and which gives this extra contribution. So you need really to understand why, or you have this shift, and Matthias Boker tried to provide an explanation why for the G-sum rule, so the spin, so the total angular momentum of quarks and gluon, you need the gravitational form factor A plus B together, and not just B, because you have this shift. And that's the same reason here. If you take just the B form, so that would be the equivalent to the B form factor, you will miss the effect from the shift, and you would not get the total angular momentum as you wish. So qualitatively, you have orbital angular momentum, but it's hard to without taking into account this shift between the true center of mass of the system and the center of P+, the quantitative speed of the target.
It would be angular velocity rather than angular momentum, but what you're saying basically is true. It's very relevant, yes.
More questions to Cedric? Okay, so it seems that I have a question. More a curiosity. Even in bright frame, we can rotate the Z direction along the momentum transfer. Some people have used this kind of frame. And then in this frame, you maximize the pairs that the photon produces, the virtual photon. Can we learn something from this kind of, because this will be from the point of view of light front, that you go to the Drell-Young condition, so that you already use it there. I mean, you boosted along Z that is transverse to the momentum transfer. So some people have used the other frame that you can go also to the time-like region. Can we learn something from that?
So I would, okay, for the light front, okay, one of the advantages of the light front that we haven't mentioned is that the charge density, but it works essentially for the charge density, you have really a number density operator. So you do not create, when you probe the system, you do not, the probe doesn't create additional quark-anti-quark pairs, and then doesn't kind of modify in a naive picture the internal structure of the system. If you go to other frames, etc., in principle, the probe, you have a contribution from the probe, essentially decomposing into quark-anti-quark pairs, and when you look at the form factors, they contain all this information all together. So that's why we can think of those distributions in the elastic frame, on the bright frame, or even if in momentum frame in general, as kind of response function to an external excitation. But we don't know whether it was purely just the charge distribution irrespective of the probe, or something that comes from the probe. Is always together, and you have the global effect. It's only that combination that is fully covariant. With the light front, it works to decompose what comes from the target and the probe, but it's only for the charge density. If you look at the different components, things do not go as well. So you have no free lunch. Here I prefer to keep covariance, but then I have the effect of both the targets and the probe, and the charge distribution is the result of their whole interaction.
Okay, so let us thank. And after that, we'll talk to us. Okay, after the section.
Thank you.
With Apeni Aguilar from Unicamp, talk about the evidence of Schwinger mechanism in QCD. Please, Apeni.
Thank you, Bis. Okay, so I'm going to talk about evidence of the Schwinger mechanism in QCD, basically about the glue mass. Many of you talk about the glue mass in a very natural way, and I was very happy, very pleased in here that the glue mass now is spoken in such a natural way. It was not so like that some years ago. And this work here is going to be like a summary of a combination of more or less 20 years of work. And the beginning of this work was done basically started here in this local, in the old buildings of the Institute of Physics, of Theoretical Physics that was here in the Principia Institute. So the last part of my talk is going to be based on in these two last articles here. So the outline is going to be the following. First, I'm going to give a brief motivation about the need of a mass, a dynamical mass for the glue. What are the difficulties to generate such a mass? Especially, I'm going to talk about a cancellation that happens that we call Siegel cancellation. Then I'm going to explain what is the Schwinger mechanism in QCD and what is necessary for to trigger these mechanisms. That is the presence of a massless pole in the vertex, in the trigluon vertex. And then I'm going to discuss how you can dynamically generate this massless pole through a Bethe-Salpeter equation, and how you can check the existence of these poles or the action of the Schwinger mechanism through the lattice simulation. And then I draw my conclusions. So let's start with the QCD Lagrangian. Basically here, actually it's not the QCD Lagrangian, it's the Yang-Mills Lagrangian. So here you have the strength tensor. And then as you know, we cannot add a mass term here in the Lagrangian because this is forbidden by the gauge invariance. So if you wanted to have a gluon mass in the QCD, it's not allowed just to come here and add this mass because gauge invariance forbids this type of term because this is going to create quadratic divergence. And then to remove this quadratic divergence, you have to add a mass term and so on. So you have a cyclic argument. So you have to find a way of generating this mass in such a way that the Lagrangian is going to be safe. And the unique way of doing that is through a non-perturbative mechanism. As you know, you have two regimes in QCD, the perturbative regime, where you have the coupling, the effective coupling is going to be small, and then is a good parameter to expand and compute perturbative objects. And then here you have a region that you can just assess it through non-perturbative tools, okay? So what are the objects that you are going to talk about in this talk? Basically, you are interested in propagators or in the Green's functions of the theory. So is the vacuum expectation of fields. Here is the vacuum expectation of the two gluon fields. That is the gluon propagator, the vacuum expectation of the ghost propagator, and the quark propagator. In the case of the quark, I'm not going to talk about anything because basically I'm going to stay in quenched QCD. So, but why I wanted to know things about Green's functions, these propagators and the vertex? We know that these Green's functions are gauge dependent, and they depend on the renormalization point, and they are scheme dependent. So these quantities have all the bad characteristics that you know. No? So are the gauge dependent, the renormalization point, and the scheme dependent. However, if you are clever enough to combine these quantities, you can construct quantities that are independent of the renormalization point, independent on the gauge, and independent on the scheme. So basically, you can construct our physical observables out of these ingredients. So they are the crucial pieces of our QCD puzzle. And what you can assess with these functions, you can assess the quark and the gluon mass. So basically, you can study the emergence of the mass scale in QCD. You can also study the bound state formation. And also, you can have some hints about the confinement through these Green's functions. And what are the non-perturbative tools that are based on first principles that can compute these Green's functions? The first one is the lattice, that are a space-time, discretize the space-time, and the precision of the lattice simulation is going to depend on the lattice space and the volume of this lattice. The other method that you have heard already here in this meeting is the Schwinger-Dyson equation. That is basically the Euler-Lagrange equations of a field theory. So you can derive formally from the generated functional, and they form an infinite tower of a couple integral equations, and they have inside of these equations the non-perturbative and the perturbative behavior of these functions. Okay, so you can describe the full range of physical momenta with this tower of integral equations. Of course, each of these methods has the pros and cons, and the difficulties with the Schwinger-Dyson equation is that every time that you are going to deal with a Schwinger-Dyson equation, you have to perform some truncations. And the problem is that you don't have an expansion parameter to do this truncation. But you have some previous studies that tells us that higher Green's functions usually give small contributions in comparison to the smaller ones. So based on this previous knowledge that you know, you truncate our series. But if you do the truncation in a casual way, you can destroy some important symmetries of our theory. In particular, here you have an example for the gluon polarization. So here you have the gluon self-energy or gluon polarization, and you know that the gluon polarization should be transverse. So this means that the gluon polarization has this tensor structure, is transverse with the momentum that it carries. And when you contract it with the momentum, this should be zero. And this transversality is a consequence of the gauge invariance of the theory. If I broke that, this means that I'm breaking the gauge invariance. So if I'm going to study the Schwinger-Dyson equation for the gluon propagator, one of the symmetries that I have to respect is to keep this self-energy transverse. Otherwise, I'm breaking the gauge symmetry of the theory. So this is one of the examples of the symmetry that you should respect. But this is not so simple as appears to be. Let's suppose that let's start with the Schwinger-Dyson for the gluon propagator in the conventional form. So here you have the pictorial representation of the Schwinger-Dyson for the gluon propagator. So this full circles here represents all the corrections that you may have in each of the propagators and in each one of the vertices, okay? So let's suppose that you are going to say that I'm going just to keep a diagram A and B, and you are going to neglect C, D, and E. What happens? If I do that, this is not even true at one loop, because you know that at one loop, the ghost loop should be included to have the self-energy transverse. So this is not, if I don't include C at one loop, this is not going to be satisfied. So, okay, fine. So I say, then I include A, B, and C, and everything is correct. No, it's correct at one loop, but beyond one loop, this is going to be wrong. And I don't want to make a calculation at one loop. I wanted to do a calculation at all orders. So, or I included all diagrams, or I cannot do anything. The problem is that these diagrams has these full vertices and the full propagators, and each one of these objects has a very difficult tensorial structure. So it's not an easy task to include all these contributions. So basically, in this formalism, it's impossible to keep the transversality of the gluon propagator. Okay, it's impossible. And this is so because the vertices satisfies Slavnov-Taylor identities. One example is the Slavnov-Taylor identities that the three-gluon vertex is satisfies, that is written here, where delta is the gluon propagator, the inverse of the ghost propagator. F is the dressing of the ghost propagator, okay, is the dressing of the ghost propagator. This H is the ghost and gluon scattering kernel that is represented here. And here you have the Slavnov-Taylor that this vertex satisfy here, okay? So all diagrams are connected through this Slavnov-Taylor, and then there is a conspiration to keep the transversality intact. So all the diagrams are talking to each other. And if I distorted or neglected someone, the transversality is going to be violated. So to avoid that, one way of doing this is to use what you call the pinch technique background field method, formalism. And what you do in this formalism in a very fast way is basically you are going to split the gauge field in a background component plus a quantum component. The background is going to respect a gauge abelian transformation, and the quantum component is going to transform as a non-abelian transformation. And this one is going to respect a word Takahashi identity because it's transformed like a abelian, like field, and this one respect a Slavnov-Taylor identity. And these always are in the external part of my diagrams. And this one can be external or in the loops. So basically, this formalism allows me to train this Schwinger Dyson here by a new series in terms of the new Green's functions in the background that has nice properties. What are the properties that this new series displays? Is the following. I can create blocks where the transversality is enforced separately. So this block here is transverse by itself. This block here is transverse by itself, and this block here is transverse by itself. So then I have a recipe how I can study the Schwinger Dyson equation for the gluon propagator, and I can truncate the series and keep the transversality intact. So I have a way of truncate and improve my truncation consistently, include the block by block, and see what is the effect of each block without spoiling the transversality. And this is so because the vertices that has this little circle here in the end that are the background vertices respect Ward-Takahashi identities. Okay? So they respect these Ward-Takahashi identities instead of the complicated Slanov-Taylor identities. So this is a big advantage. And the price that I have to pay is to translate the background gluon propagator to the conventional gluon propagator is to compute an auxiliary function. Okay? And this function I can compute, and it actually is related to the ghost propagator. So let's talk about the dynamical mass generation in this background formalism. So you have, in the last 20 years, you have an accumulation of evidences that the gluon self-interaction generates a dynamical mass. And this evidence comes from basically the lattice QCD. Basically, what you see is that the gluon propagator saturates in the deep infrared. So here you have the lattice data, and you see the saturation of the gluon propagator here in the infrared. So why this saturation implies in a gluon mass? So here you have the gluon propagator. This simulation, most of them are performed in the Landau gauge. So if I write the tensorial structure of the gluon propagator in the Landau gauge, it's like that. And here you have the scalar part. So you can write the scalar part in such a way. In the limits of Q goes to 0, this goes, and then this means that you have 1 over m squared. Okay, so this saturation is a sign that you have a mass. Okay, so these many different groups from lattice have seen this design, but this was proposed many years ago, much before the lattice. Well, lattice was giving the first steps. The proposal of a gluon mass, it was first done by Mike Cornell in '82. So it was a theoretical proposal, and afterwards it was confirmed. So what you expected? This gluon mass cannot be generated by perturbation theory, because once that you have in perturbation theory, you have said that you cannot put a gluon mass in the Lagrangian. Our mass is 0, so there is no way of creating a perturbative mass out of perturbation theory. And you know that when you perform any perturbative calculation, you are full of unphysical divergences that is due to the presence of the Landau pole. Okay? And if you wanted to extend the validity of these perturbative calculations, most of the tricks that you do is to put a hard cutoff there in the calculation to cure these unphysical divergences that are present there. So one example here is the perturbative gluon propagator that you can see here displays this Landau pole in the lambda QCD scale. So this mass, the presence of the mass that is going to be a pure non-perturbative effect is going to cure all the divergences non-perturbatively. Then you have to pose the first question. How one can generate a gluon mass or see the saturation in the gluon propagator without breaking the gauge symmetry? The point is the following. QCD is going to have a similar cancellation that protects the gluon to be massive as happens in QED. What is this mechanism? Is what you call Siegel cancellation. So each one of these blocks here in my reorganization, I have a protection that is the Siegel cancellation that does not let us to have any quadratic divergence. And is basically this cancellation here. Every time that I have this combination of these terms, I have 0. Okay? And this combination also happens in QED. And it is exactly that it protects the photon to be massive. Is this cancellation that protects us from break the gauge invariance in QED. So here in this block, I have the ward identity for this vertex here in red. When I sum the ward identity that this vertex satisfies plus the Siegel identity, the inverse of the gluon propagator at 0 is 0. So no way of getting a mass. The same thing happens in the yellow block, and the same thing happens in the two-loop dressed diagrams, that is this blue diagrams here. Always is this cancellation that is triggered. So how you can see that? You can see that in a very simple example, that is the scalar QED. Is a prototype, no? It's exactly, the mechanism is the same, it's just the indexes is going to be a little bit more complex to do in QCD. So here you have the one loop diagrams that enters in the vacuum polarization of scalar QED. So this vertex here, photon scalar, satisfies this ward identity, this ward Takahashi identity here. So I hit you with the momentum that the photon carries the vertex, and I get the subtraction, the difference of two inverse scalar propagator. Okay? Then in the limit of Q goes to 0, this ward Takahashi identity becomes a ward identity that is given by this expression here. Fine. So let's compute the sum of these two diagrams that are transverse. Is D1 and D2 are transverse, so I can factor out the transverse projector here, okay? And then, since it's transverse, then does not matter if I get the G mu or the P or this component. So I'm going to compute this component here that is easier, here, okay? And then in the limit of Q goes to 0, that is the limit where I can see any mass, okay, that I'm interested in. I take the limit of this expression is exactly the limit where the vertex appears in the word identity here. So I replace the word identity result here. And then D1 becomes that. I sum D1 and D2. What appears? The SIGO identity. So this is the way that the SIGO identity happens in the scalar QED, is the way that it happens in QED, conventional QED, is the same way that it happens, is going to happen in QED, in QCD, okay? I'm not going to show in QCD because it's going to be exactly the same thing, just a little bit more difficult because of the indices. So then comes the question 2, how you can evade the SIGO cancellation and create this glow mass? The answer to that is to introduce the massless poles and trigger the Schwinger mechanism in QCD. What Schwinger said to us? Schwinger said that a gauge boson can acquire a mass if the gauge symmetry forbids a mass term at the level of the fundamental Lagrangian, provided that its vacuum polarization function develops a pole at 0 momentum transfer. What he's saying here? He's saying basically the following. If I have the vacuum polarization, pi here, and the vacuum polarization develop a massless pole of this type, 1 over q squared, I replace my vacuum polarization here in the propagator, and then what I get in the limit of q goes to 0, something with mass. So the vacuum polarization should acquire a massless pole. How I can make this vacuum polarization acquire these massless poles? The vertices that belongs to this appeared in this vacuum polarization should have this massless pole. Okay? So in this case here, I'm showing a photon case, no, a photon example, a photon propagator, no? In our case, it's going to be the trigluon vertex. And of course, this pole, this massless pole, should be a non-perturbative, or should have a non-perturbative orange. So let's see how you can generate this, how this works in QCD. Here you have the trigluon vertex, and then I can split my trigluon vertex in a pole, a part that does not have pole, and a part that has the massless pole that I was talking about. Okay, so the yellow does not have any pole, and then this part here has this massless pole, this V. So the V I can write as a Q alpha over K squared, the massless pole, times a function C. This V component of the vertex should be longitudinal couple for not appearing in the asymmetrics of QCD, because I don't want it to create any physical state, new state, massless, okay? And it also is transversally projected. The transversally projected version should be 0. And what happens with the word identity, the word Takahashi identity that the full vertices satisfy? what the presence of this massless pole is going to do with the Ward-Takahashi identity. Okay, so then the Ward-Takahashi identity should be satisfied in the same way. So here I have the Ward-Takahashi identity in the same way, satisfied. So when I hit with the Q, the right-hand side of the equation, I have this, and this is going to be equal to the difference of the two propagators. Then I do a Taylor expansion to see what happens in the limit of Q goes to 0. That is the limit that I'm interested, the limit of zero momentum now, to see what happens when in the origin. And then you see that my vertex is going to be the previous answer plus a displacement, minus in the case. A displacement here that is related to that function that appears in the pole. And this function I'm calling CFAT here. Okay, so this CFAT is completely related to the presence of the poles in the vertex. Okay, so I come back to my Gloom-Schwinger-Dyson equation and replace my 3-Gloom vertex by a part without pole and a part with pole. So here, I come here and replace that. So these two is going to trigger the seagull cancellation as before, and the red and the green one that has the pole is not going to be 0 anymore. It's the new contribution. And it is precisely this one that in the limit of Q goes to 0 that is going to create my mass dynamically. So in the limit of Q goes to 0, the inverse of the Gloom propagator is going to be proportional to this CFAT that is the pole, is related to the massless pole that I include in my 3-Gloom vertex. So the saturation of the Gloom mass is related to the presence of this massless pole. The problem is that now how the dynamics is going to generate this massless pole. The 3-Gloom vertex has its own Schwinger-Dyson equation. And I have to check if the Schwinger-Dyson equation of the 3-Gloom vertex allows me to have this massless pole to be created dynamically. So I come here and I replace the part without pole and the part with pole. And then for the part with pole, I have a Betz-Salpeter equation that governs the creation of this massless pole here. So this is the equation that describes the formation of this CFAT, that is the formation of this massless pole. So I studied this Betz-Salpeter. If I found a solution for this equation, I have the answer, yes, my dynamics allows me the formation of this massless pole. I have strength enough for creating this massless pole. And it was precisely that what you did. You studied this equation. I have not showing here the details of this kernel here. And then you is a eigenvalue problem. The coupling that you use is 0.3. The renormalization is 4.3. And then the mass is going to be related to the inverse of the propagator and the CFAT, and then this is the answer for the CFAT that you found. So basically, you found a way that the dynamics allows the creation of these massless poles dynamically. And then comes the last question. Is there a way to confirm the action or the action of the Schwinger mechanism in QCD using just LATSI results. So you are going to see this signal through the displacement of the word identity. So when the Schwinger mechanism is off, what happens? Here you have the word Takahashi identity. When the Schwinger mechanism is off, I don't have poles, right? So when I take the limit of Q goes to 0, I have this word identity, and then this is the limit, and then I can connect this limit with this quantity here that is a projection in the soft gloom limit that we can compute. This is done in the scalar QED case. That is just to show you in a simple way how this works. This is a projection of the form factor in the soft gloom limit. So this usually LATSI can have access in normal QCD. When Schwinger mechanism is on, I have a pole-free part and a pole part. When I write the word Takahashi identity, I have the displacement. So I have this correction here. So what happens is the following. My form factor is going to be corrected by the displacement. So the LATSI, if LATSI can compute this, is going to see the signal of this displacement in the form factor. Okay? So is this that you are going to looking for? What happens in QCD? In QCD, is not a word identity, but is Lanov-Taylor identity, so it's more complicated. So the displacement can be expressed in terms, in this expression here. So this is a form factor of the trigloon vertex in the soft gloom limit that is computed. This is the dressing of the ghost propagator in the 0 limit that also is computed on the LATSI. This is the inverse of the propagator, the gloom propagator, and the inverse of the derivative that you can compute with the LATSI data. And this W is the derivative of the ghost gloom scattering kernel that is not computing using is not computed on the LATSI, but you can compute using Schwinger-Dyson equation using using LATSI inputs. And you have done that, okay, in this work. And here is the result of the C, the signal on the LATSI. So here is the construction of that function based on this LATSI's result. So that is a clear evidence of the signal of the Schwinger mechanism on the LATSI calculation of the form factor of the trigloon vertex. So then I have here my conclusions. So although the QCD Lagrangian appears very simple, there is a lot of complex dynamical effects hidden in this Lagrangian, and one of them is the emergence of a gloom mass, and then you see that the gloom self-interaction is going to generate a dynamical gloom mass, and then the poles in the trigloon vertex is going to generate this gloom mass, and then creates this displacement in the word identity, and the displacement of the word identity is completely related with the Betz-Salpeter amplitude, that's CFET that I was talking about, and then you have a signal from the LATSI that corroborates the action of the Schwinger mechanism in the emergence of the gloom mass in QCD. So is that.
Questions to Arlene? Okay.
Well, very nice talk. One of the clearest talks that I have heard in this topic. Congratulations.
Thank you.
So, so you would say that the same cannot happen for the photon, isn't it? Because photon is not a self-interacting field. Otherwise, there is a way to generate mass for photon as well.
In 2D, you can put a massless pole. That is the same mechanism. Now, Schwinger mechanism works for 2D there. No, but then if you put a massless pole in the polarization, then you can have. But you don't want it to do that, no, because you know that the photon is not going to does not have this dynamical effect.
I was just imagining if it's a quantum electrodynamics where we just by hand put a large coupling. If it were living in a universe with large alpha, would that be possible?
Yes, you could. But the point is the following. After that, you have to check if your Betzel-Peter that is going to govern the creation of this bound state is going to to have the strength to create these poles. This is precisely this point here of this block of the talk, no? If I come here and I solve this equation, and this equation say, no, QCD does not have strength for generating this massless pole, that's the end of this mechanism. I stop this story, and then there is no, I falsify all this story of the Schwinger mechanism for QCD. And here is precisely what you have proved. You know? So there is blocks that was proved in parts. You know? So first you have the massless pole. You say, okay, let's suppose that you have the massless pole. Works. Then you have to see if you have strength enough for creating the dynamical poles through the Schwinger diason for the trigon vertex. And then you see, okay, fine, it works.
Just one more question.
But QED is not going to happen because of the coupling, no?
Yeah,
most
I was
likely.
just thinking that if you by hand replace it 1/137 by say 10, would it work or not? But I think it will be maybe an interesting theoretical
if you put a fake coupling, yes, maybe no. But
so one last question: when we usually think of gauge bosons like W's and Z's, so when they acquire mass, we associate with them getting another extra polarization, the longitudinal polarization, and another degree of freedom. How does one view the gluon with a mass?
That's a good question. I don't know how to answer this question. This is something that is another part of this puzzle, how you are going to deal with the polarization in this dynamical picture, because perturbatively, this mass goes to 0, right? And then you are forced to have just 2 degrees of freedom in the polarization. You have just to have 2 polarization. And then non-perturbatively, you have 3. And how this dynamically is going to work? I don't know how to answer this question. And if you sum 3, perturbatively, you are going to destroy everything that you have perturbatively computed. And so this bothers me, and I don't know how to answer this question. It's a very good question, and honestly, I don't know how to answer. It's something that is in the list of how that you have to put another question in this list to answer.
More questions to Arlene?
Sorry if I missed it, but I was wondering, would there be any other place where you could put the massless poles and get the same sort of effect?
Actually, all vertices in QCD is going to have this massless pole. Okay. I concentrate on the trigon vertex because these are going to be the most important for the generation of the gluon mass. the dominant part contribution is going to come from that, but then the four-gluon vertex is going to have, the quark gluon is going to have, the ghost gluon vertex is going to have, but the contribution for the gluon mass is going to be smaller. You have done for the ghost gluon, that is simple and is very small. The quark gluon, you are about to finish, this is small. The four-gluon is a kind of hell. And is in the plane you are started to do, but it's a hell, really.
Okay, Cedric.
So just a question about the C of R square function that you proposed, which then you combine different information from lattice and then a little bit from Dyson-Schwinger.
And this one here, right?
Yes.
You want
So
this one here.
yeah. So if everything goes right on the calculation side, then you can interpret the result as a signature of the appearance of this massive part. But if something goes wrong on the calculation side, you cannot conclude that this is indeed the presence of a massless pole.
And what you mean wrong?
Well, I mean, I don't know on the that's some approximation, because lattice there are always approximations. Then you also
You
use some
mean on the lattice?
Yeah.
Well.
So it's just that it's a nice thing, but I don't know if we can directly conclude that this is really.
You know, this form factor is a kind of a form factor that was computed. I just put this reference here, but it's a form factor that was computed by many groups, and of course the scale is not exactly the same for them, because you have to match the volume, you have to match many things, but the shape is all of them agree. So I don't think that there is room for saying that this calculation is wrong, at least in the qualitative picture. I don't see room for being wrong the shape, no? Maybe you can have something of a small detail, but then the result that you see for this C fat here is not a very small signal that you are seeing. You are seeing a big one. No? So then even if the lattice has a change from one lattice to the other, I don't think that this is going to be affected by that, you know. If it was a lattice calculation that it was more complex, I would agree with you, but this one apparently is trivial to get. No, for this kinematic configuration is not. For others, I think that it would be harder to get. And you have more groups that got that. Maybe there is a fact or something that is going to change, but nothing so dramatic. Well, I think that there is no lattice on QED, right? So if they had, would be nice. Yes. Yes, actually, I could say that. Yeah, it's not a bad idea, really. Yeah. Thank you.
So let us thank Arlene and our colleagues from the morning. We reconvene at 2. Okay, I think we have enough time to lunch. See you.